All right, so welcome to Math 150 Multivariable Calculus. This is lecture 19. We're going to do integration in two variables. We'll talk about polar and spherical. We'll talk a little bit about Kabini's theorem. I think this is the hardest lecture in the semester because of the discontinuity of a 2-week spring break. And if you think about what proportion of the semester you've spent away versus what proportion you've actually spent in class, given that this is the 19th lecture, okay, then that means we had 18 before, 3 lectures a week, that's 6 weeks. So 25% so far to date has just been on break. So it takes a while to get a little bit up to speed. Over the next week or two, we are going to have a couple of days where you're going to have to watch 2 videos. You can, of course, if you want, watch some of the videos at your 1.25 or possibly even 1.5 speed. We need to make up a little bit for the fact that we have a little bit of extra review in the first week. I'm trying to keep the amount of homework reasonable, that the number of problems is not overwhelming. The homework is also always on material that we've already covered, so you should feel free to look at it, see what homework is coming down the queue. Can I get it out of the way and get it done right now? So what we want to do is we want to talk about how do you integrate in 2 variables. We could develop rigorously the theory of integration in 2 variables, similar to how we developed the theory in 1 variable. I am going to elect not to do this. This is Math 150. If you really want to see something like this, become a math major, you'll take a real analysis class, take a measure theory class, and we'll really develop the theory. Or if you want, just email me, happy to meet with you and go through things more rigorously. But the main idea of integration in 2 variables is you have some region, and we chop up the region, say, into a bunch of rectangles. And for each rectangle, we find upper and lower sums. Because we have a surface above this, and we'll get upper and lower volumes, and we'll add them all together. And then we take a finer and finer mesh. So what we might then do is we might take each one of these and divide each one of these up further and keep going and keep going and keep going and hope that something converges. Is this enough level of rigor to just get a sense of what's going on? Is we basically repeat the process in 1 dimension and we just do more bookkeeping. Things become a little bit harder. We don't quite have the same version of the mean value theorem, but we have other things that we can use, and we can, for the most part, make all the arguments work similarly. You typically have a choice in life, and it's not between 2 good options. It's the lesser of 2 evils. Do you want a horrible region of integration, but a nice function, or a nice region of integration and a horrible function? Which do you think typically is better? So that's one possibility. What else? I'm sorry, and that's the other possibility. It's going to depend a little bit on the problems. As a rule of thumb, I often prefer a nice region to a nice function, but it's going to depend on the problem. So can someone give me the equation of a circle? Good, and if I do less equal to 1, it's going to be the filled in unit circle. If I were to write this in polar coordinates, what would this be in polar coordinates? So this is Cartesian. What would it be in polar? X squared plus y squared is less equal to 1 is a circle in Cartesian coordinates. What would it be in polar coordinates? Okay, so you could get r squared cosine squared theta plus r squared sine squared theta is less equal to 1. Well, what's cosine squared plus sine squared? So you get r squared is less equal to 1, right? But r is non-negative, so if r squared is less equal to 1, yeah, so in polar coordinates, this unit circle is just r is less equal to 1. So if I were to plot this in polar coordinates, this is what I would get. What shape is this? Rectangle. So if you remember your geometry, it's impossible to square the circle. If that means anything to you. But if we change coordinate systems, so in polar coordinates, a circle is actually a rectangle, which is the nicest region of integration possible. What do you think a sphere is in spherical coordinates? Almost. Not a cube. I wouldn't call it this. So a cube is a very special where the length, width, and the height are all the same. Rectangular prism or box, something like that. So when you say cube, all the sides have to be the same. And so here, this is not a square, because my theta goes from 0 to 2 pi. And my r goes up to 1. So this is the advantage of spherical coordinates, is a sphere now becomes a box. And the hope is that we can do integration nicely. So if you have a rectangle, the idea is, let's say the rectangle looks like this. Here's the point AC, here's the point BD. And so the other points would be BC, and then this would be AD. And I want to integrate over the rectangle R. So we'll write the double integral of R of f of xy dA. What do you think A stands for? Why do you think I'm using the letter A? There we go. So you should always choose letters that are meaningful so that you can glance down and see what's going on. So what this really means is I chop my rectangle up into lots and lots and lots of pieces, and I do my upper and my lower sums, and I have things converge. If you want to do this, you need help. We can get it for you. You should not want to chop things up into lots and lots of pieces. Right? In Calc 1, do you want to chop things up, calculate the area of each little piece, and then do some kind of limit? No. It's similar to when you do a derivative, you don't want to go back to the definition of the limit. You want to use your rules of calculus. So we never want to compute this by chopping things up. And the big result in multivariable calculus is that, well, look, if we have something like this, this is really the same as the integral y goes from C to D, integral x goes from A to B, f of x comma y dx dy. And it's also the same as the integral x goes from A to B, y goes from C to D, f of x, y, dy, dx. This is not always true. This is the hope. If your function is nice, this will be true. That essentially when you're chopping things up, it's equivalent to, look, fix a value of y and then calculate what is the contribution as I move horizontal. And then add all of those contributions for all the different values of y. That should be the same as calculating, fix a value of x and go vertical, find the value of that, and then add all the different verticals. If I put a bunch of money on the table in a lattice structure, if I add all the rows and then add those values, should that be the same amount of money as adding all the columns and then adding those column values? Your numerical wealth should not change depending on the order in which I add the pennies, dimes, nickels, quarters, whatever. Out of curiosity, how many people actually have money on them right now? Just curious. You have crypto, right? This is what I'm on. I actually do have coins. One of the reasons I have coins is just as a math professor, I need to, at a moment's notice, be able to toss a coin if necessary. And so I always have multiple coins on me for mathematical emergencies. So if you have a finite amount of money, it shouldn't matter how you rearrange things. If you have an infinite amount of money, however, it could actually matter how you arrange things. So the big dangers we have in mathematics is whenever you have an infinity, you have to be careful. And so the big result we have is Kabini's theorem. And so then it says the following: if the integral of the absolute value of f of x, y, dA is finite, then in that case, then this is true. So if the absolute value is finite, then we can switch, the order in which we do this. Okay. I am not going to prove the Kabini theorem. So another way of saying the Kabini theorem is if either one of these integrals is finite, when you integrate the absolute value, you can switch. So if either integral of the absolute value is finite, then can switch orders. If I have two variables, how many orders of integration do I have? How many ways can I choose the order of integration? Two. What if I have three? How many orders are there now? Six. I have three choices for the first, two for the second. If I have four, how many are there? So as you have more and more items to integrate, you have more and more choices, and it's going to get harder and harder. If you only have two, and you're doing an integral over a rectangle and it's not working, what should you try doing? Switching the orders of integration. This is one of the major techniques of multivariable calculus. Switch the orders of integration. I may have a video of one of my kids waving their magic bubble wand, yelling, switch sums, to just, this is what you do. You just switch the order of integration, everything works out beautifully. Why? Because these are cookbook problems on exams or homeworks. So something has to work. In the real world, most integrals can't be done. And that's why in the near future, we're going to have a lecture on Monte Carlo integration. What do you do when you can't actually integrate in closed form? And we will actually learn, because this is how a lot of integrals are done in practices, we numerically simulate them and approximate them. They're just too hard. And in a lot of financial mathematics, you have to do 360 dimensional integrals. And we're not doing this in closed form. So we have to find really good ways to numerically approximate very quickly the value of these integrals. But for a lot of cookbook problems, if we're integrating over a rectangle or more general shapes, we'll talk about what is a more general shape where all of this works. One of the main techniques we have is switch the order of integrations. If one order doesn't work well, try the other. This is similar to the techniques we have in calculus. When we're trying to do an integral, try partial fractions. Is that the first thing you try? Unless you have something that looks like a fraction, in which case maybe you should try partial fractions. But this is one of the last things we try. Use substitution, integration by parts. These are the more go-to ones. And you just start trying the different things. I'll give you an example of where Kabini can fail. So what I'm going to do is, rather than doing a double integral where you can't switch the order of integration, I'm going to do a double sum where you can't switch the order of integration. Rather than doing a double sum, I could smear things out and make it nice, continuous, and integral. But that's more work. It's very clean to do it as a double sum. So if I can show you a double sum that fails, you can push this forward and turn these into continuous functions. So I'm going to define the thing as follows. In the interest of time, I am not going to draw all infinitely many dots. I will only draw finitely many. I'll draw one row after this. And it goes off to infinity. So this is the point 0, 0, 1, 0, 2, 0, and so on. This is going to be the point 0, 1, and so on. And I'm going to define it to be plus 1 here, minus 1 here, and then 0 for all eternity. And then in this column, I'm going to do 0, plus 1, minus 1, and then 0 for all eternity. And then 0, 0, plus 1, minus 1, and then 0 for all eternity. So is it clear what the pattern is? So I want to study the sum, m goes from 0 to infinity, n goes from 0 to infinity of a, m, n, versus the sum, n goes from 0 to infinity, the sum m goes from 0 to infinity of a and m. Note the double sum over n and m of the absolute values equals what? So if I just sum the absolute values, what do I get? Not 0. I'm summing the absolute values. Infinity. Right? I have infinitely many terms that are 1. So this is an example where there's an infinity. And anytime you have an infinity in mathematics, that is a warning sign that you have to be careful. What does each column sum to? 0. So if we fix a column, we get 0, and then we sum over columns, and then we get 0. What about the rows? If we fix a row, what do we get? Except for the first one. What's the first one? So if we fix a row, get 0, save the first row is 1, sum over rows, and we get 1. So if we fix a row and then sum over rows, we get 1. If we fix a column and then sum over columns, we get 0. So this is an example where we cannot switch the order. If you don't like this because it's discrete, what you could always do is take the function that's 1 at 0, 0, and draw a circle of radius 1/2 centered at that point, and draw like a cone coming up like that. And where it's -1, you draw the cone going down. So you'd have positive cones and negative cones. So you could make this into a continuous function and give yourself a real honest to goodness example. So this, I think, is enough for your first course in the subject to just illustrate how dangerous things are. You have to make sure that one of the integrals is finite. As long as one of the integrals is finite, you're okay. This goes back to the limit laws. What is the limit of a sum? What should the limit of a sum be? What should that equal? So for logarithms, the log of a product is the sum of the logs. You need to be able to explain what would the limit of a sum be? It should be the sum of the limits. Should be a limit as n goes to infinity of an plus the limit as n goes to infinity bn. If at least one is finite. What's the limit as n goes to infinity of n squared minus n? As n goes to infinity, what's n squared minus n? It's infinity. You could write this if you wanted as the limit as n goes to infinity of n times n minus 1. This is clearly infinity. If I give you the limit of n squared, of n minus n squared, so the limit as n goes to infinity of negative n times n minus 1 is negative infinity. If I give you the limit of n squared minus n squared, this is just 0. I give you the limit of n squared plus c minus n squared. That's just c. I can make the limit whatever I want, but if I were to split it up, I would have infinity minus infinity. Infinity minus infinity is not something we can deal with. We don't know what infinity minus infinity is. As long as one of the expressions is finite, then the limit of a sum is the sum of the limits. But if both expressions blow up, I can't say the limit of the sum is the sum of the limits because I could have infinity minus infinity. I don't know what infinity minus infinity is. So instead of a do not fly list, we'll have the do not compute list. Which expressions can we not compute in mathematics? So infinity minus infinity, we just said that's something we can't do. What else can't we do? I'm sorry? Well, 3 over 0 would be infinity. So I'm willing to possibly allow 3 over 0, but there's something over 0 that I might not allow. 0 over 0. So 0 over 0 would be bad. What else would be bad? So 0 to the power of 0. What else? Sorry? I can work with complex numbers. I've taught courses in that. That's okay. 0 factorial, we define that to be 1. It's like Seinfeld. There's one way to do a TV show about nothing. So what would 0 to the infinity be? So we'll put 0 to the infinity down. There's something else involving infinity twice. Yeah, infinity over infinity. We should not talk about that. And then there's something else involving 0 and infinity. No, infinity over 0 would just be infinity. To the 0 power. So we could possibly do infinity to the 0. As to what does that mean? There's another more common one. No, 0 over infinity would just be 0. I take something really small and I divide it by something really big. No, but infinity over 0 would just be even bigger infinity. Infinity times 0. So yeah, we have to be careful whenever we see anything like this. And when you did algebra 2, you should have had fears every time you have a denominator. Is the denominator 0? If the denominator is 0, I've got to be careful and worry about doing this. Okay, so the idea is if we have a rectangular region, we can integrate over the rectangular region without any trouble. So I think the problem I do in the video is the following. So I want to integrate f of xy is x cubed y plus e to the is that e cubed x? Okay, e cubed x, we'll do e cubed x plus cosine y over rectangle. So the first thing is the rectangle infinite or finite? It's fine. So one of the dangers of having an infinity is if I'm integrating over a region of infinite area, then a finite function over a region of infinite area could give me infinite value. Okay, is my function continuous? Does my function blow up at all in this region? No. In fact, I can bound my function. If I look at f of xy in absolute value, this is the absolute value of x cubed y plus e cubed x plus cosine y. This is less than equal to x cubed, absolute value of y, plus e cubed, absolute value of x, plus the absolute value of cosine of y. And so x is between 0 and 1, y is between 0 and 2 pi. How large can x cubed be? 1. How large can y be? 2 pi. The next term is plus e cubed times 1. And how large can cosine of y be? 1. So does everyone agree that this is less than 2020? I'm sorry, it's 2022. 2022. It's much less than that, but I don't really want to figure out what is 2 pi plus e cubed. So if I just take something like 2022, that's clearly larger. So I now know that the integral of the absolute value of f over this region is finite. The function is bounded, the region is bounded, it has finite area. I'm in great shape. So now I just have to do the integration. All right? So let's integrate. Do you want to integrate with respect to x first or with respect to y? Okay, so then that means I'm going to go y goes from 0 to 2 pi, x goes from 0 to 1, x cubed y plus e cubed x plus cosine y dx dy. And I can put the brackets here to remind myself I'm doing this x integration first. And when I finish the x integration, then I do the y integration. How long did it take you to learn how to calculate a partial derivative? Did it take you that long? Come on. Less than a minute, right? Less than a minute to calculate a partial derivative. Once you know how to do a derivative. Basically, the secret of partial differentiation is, well, look, just treat all the other variables as constant and then just differentiate normally. So when I'm doing a double integral like this, y goes from 0 to 2 pi, x goes from 0 to 1. As I do the x integral, y is fixed, y is a constant. So I just do my integration first with respect to x, keeping y fixed. Then I'll integrate with respect to y. And that's multiple integration. Then we'll learn some techniques to handle more complicated regions. So we now start doing things. Notice that unlike Calc 1 and 2, I'm actually putting subscripts in my integrals. I'm saying x goes from 0 to 1, y goes from 0 to 2 pi. Why am I doing this? There should be a reason why I'm putting the x's and y's there. To make sure we know the order, to try to minimize the chance of doing things wrong. When I write it like this, dx dy, because the dx is first, we should be doing the x integration first. So that means these bounds over here are the bounds for x. I don't have to write x equals 0 to 1. It's understood that x equals 0 to 1. Any physics majors here? If you go deeper in physics, you might see like Einstein's summation convention, which came up in general relativity when you have tensors and you have an upper index and a lower index, and you have two such things hitting each other. It's implied that there's a sum that happens. So this allows you to save some space and not write the summation sign. As you start to get used to notation like this, it actually can become useful. If you're really comfortable, there's no need to write x equals 0 to 1 because we know the first integration has to be with respect to x because dx comes first. The amount of extra work to write x equals and y equals is minimal. Especially when I'm doing it electronically like this. The cost is so small and it allows you to glance down and see what's going on. I highly advise doing this. So now we would have, it's the integral y goes from 0 to 2 pi. Now let's do the x integration. So we have x cubed y. Can somebody tell me what is the integral of x cubed y with respect to x? So what function, when I differentiate with respect to x, gives me x cubed y? One-fourth x to the fourth y, and I evaluate this at 0. I could, of course, have a plus c if I wanted, but because I'm evaluating at 2 points, the plus c would cancel. So I might as well take the simplest possible antiderivative. What function has derivative e to the cubed x?
Cube x squared over 2.
So 1/2 e cubed x squared at 0 and 1. And then the last is what function has derivative cosine of y when I take the derivative with respect to x? X cosine 1 at 0 and 1. All right, so now it's the integral y goes from 0 to 2 pi. 1/4 x to the 4th y when x is 1 and 0. Okay, well, when x is 0, everything's going to cancel. So I'm just going to get 1/4 y plus e cubed over 2 plus cosine of y. Okay? Hopefully I haven't made any mistakes. So now what function has derivative 1/4 y with respect to y? One eighth y squared at 0 and 2 pi. E cubed over 2, I'll do that one. That's going to be e cubed over 2y at 0 and 1. And now what function is derivative cosine of y?
Or negative.
So it's going to be negative sine of y. And as a test, what's the derivative of sine? The derivative of sine is minus cosine or plus cosine? Plus cosine. So I think we actually want plus sine. Because the derivative of sine is cosine. Now, you are actually quite fortunate, well, this is 0 to 5, because your mistake would not matter. Because what's the integral of cosine over a full period? 0. So if I have an extra negative sign, it's not going to make any difference. You will still get the right answer. And if you have a professor who's grading and just saying, did you get the right answer? You would have the right answer. If you have a professor who's being very careful and checking every single line, it would be caught. How many of you remember Snell's law and stuff like that? When you have light going between two different media and refracting an angle. So when I was in high school, I took a physics class at Harvard, and I had something going through two different media, and I made a sign mistake, but then it went back out to the same kind of media as the first, and so the two signs canceled, so the final answer was right. So all the mistakes canceled, and I had the right answer. So a lot of times you can get the right answer by doing wrong work in between. So you want to be very careful, and if possible, can you always check and see, do things look reasonable? For cosine, cosine is a positive function, at least when y is small. So if we integrate cosine from, say, 0 to pi halves, that should be something positive. And so sine of y is going to be positive in that range, and it's going to be getting larger. So we see that we really do want to have a plus sign over there. All right, so when we put this all in, we get y squared, which will become 4 pi squared, so it's going to become pi squared over 2 plus e cubed pi, and that would be the answer. So this is the simplest type of integration we can do. Things get harder as we have more painful problems to look at. And then it becomes a question of which is the easiest way to do. But any questions about the general technique? Integration two variables pool, okay. So then the question becomes, what if I give you a more difficult region of integration? So this will be a little bit of work to prepare for future lecture. So let's say I give you this region. Here's the line y equals x. And I want this region. Do you think a triangle should count as a nice region? If we can't handle integrating over a triangle, we're in trouble. Right? If the only thing we can handle is rectangles, we're dead. A triangle is not a bad region. Now, when I view this, one of the ways I can view this is I can fix a value of x, and then I look and see what is the range of y for that value of x. What's the other way I could do it? So that's fixing a value of x and looking at the range for y. What else could I do? So one is fix x and see how y varies. I could fix y and see how x varies. So maybe I fix y to be over here, and now I see how x varies. So in the first case, we fix x. So y goes from where to where? So y goes from 0 to x. So we would get, if we call this point 1, 1, we'd have the integral x goes from 0 to 1, and in the integral y goes from 0 to x, f of xy dy dx. And the reason it would be like this is because we first fixed x. And so because we fixed x, it's okay if the y bounds of integration depend on x, because x is just some fixed number at this point. And then we let x vary. The other way we could do it is we could first fix y. And so we fix y, what does y range from? So what would be the range of y? 0 to 1. And now what's the range of x? We didn't write this one, so let's figure it out. So if we fix y, what is the x range? So if you fix a value of y, what's the first value of x that you have inside the triangle?
Of y.
Y. Y is the first. And now I'll ask, what is the last value of y? So what's the last value of x? The fixed value of y. You start at x equals y, and where do we end? End at 1. So x would go from y to 1. And so x goes from y to 1, f of xy dx dy. And so this is how we would integrate a nice function over the triangle. So the triangle has finite area. So if my function is continuous, any continuous function is going to be bounded. I can use the Kabini Theorem. I can do either integration. I am not going to go through the proof that you can divide this up into squares or rectangles and then show that you can rearrange them and it doesn't matter. This should make intuitive sense. So we're doing these slices. And I can either slice things horizontally and add the horizontal slices, or I can slice things vertically and add the vertical slices, so long as everything is finite. As soon as there's an infinity, then it's game over and you have to be careful. But because everything is finite here, we're in really good shape. The hope is that one of these two integrals is nice. And that you will have some homework problems where almost surely you will be given a region, and I will tell you, do the x integral from here, the y integral from here to here, and it's not going to work out. So what should you do? Switch. If you have a double integral, there's really only two things to do. Do x first and then y, or y first and then x. Okay. So the question then becomes, what is the most general shape that is nice? We all agree rectangles are nice. Triangles, they're not too bad. If I gave you a parabola, that wouldn't be too bad either. So the real thing we want is we want a shape where I can fix x and see the range of y. Or conversely, fix the other one. Did I say fix x? Because we wanted to fix y and see the range of x, we'll fix x and see the range of y. So what we really want, what we're looking for, and we'll talk about in the later lectures, is we want shapes where one variable goes from, say, alpha to beta, and other has a nice, well-defined start and end. So if I gave you, something like a parabola, y equals x squared, and let's say this is the point 0, let's say this is the point 3, just to have some fun. So x goes from 0 to 3, and then for a given value of x, what would y be? So if I tell you I have a value of x, what does y start at and what does y end at? Well, let's look at the picture. Where does y start? Y starts at what value? 0. And y goes all the way up until we hit the curve. The curve is y equals x squared. So when we hit the curve, what's the value of y? Well, we're starting at x, not at 3. It would be x squared. So y would go from 0 to x squared. And we would have f of xy dy dx. So does everyone see that if I was trying to integrate under the parabola, if I fix x, this is what I would have. I could now play the game the other way, and I could fix y. So I would have the integral, y goes from what to what? So what's the smallest value of y? What's the largest value of y? 0 is the smallest, excellent. And what's the largest value of y? 9. And so now, when I fix a value of y, I've got to ask, what's the smallest value of x? What's the largest value of x? Which is the easier one, the smallest value of x or the largest value of x? I think largest. No matter what value of y you choose, what's the largest value of x? 3. So I think that's the easier one. Now, if I give you a value of y, what's the value of x that corresponds to that? No. Root y. Y equals x squared. So I need to flip the relationship. So this is the same as x equals the square root of y. So if I view this as a function of x, I have y equals x squared. If I view it as a function of y, it's x equals square root of y. So I would say x would go from the square root of y to 3, and it would be f of xy dx dy. And that would be how I would integrate over the parabola. And these curves, we will later see that these are examples of what's called simple regions, where they have a clear bottom and top. You enter, stay in the region, and then leave and never come back. And you can either do that by coming from below and exiting up, or from coming from the left and exiting to the right. Does anybody know an example of a region where if you're coming up, you enter the region, stay in the region, leave, and then come back, stay in the region and leave? Well, I need a nice figure. Ellipse would actually be fine because you would enter the ellipse and then leave. But something related to ellipse. If you know Homer Simpson, I might be able to give you some advice. Donut, yes. Right? What would a donut look like? Here's the donut. If we tried to enter it, we would enter it, then we leave, and then we come back. And similarly, if we tried to do it in the other direction, we would have trouble. There is a solution to the donut. What could we do to make the donut region nice? There's two possibilities. Fill in the hole. But I don't want to integrate what's in the middle. I only want what's in the donut. So what could I do if I fill in the hole?
Good, you can create the hole.
Good. So one possibility is to fill in the center, integrate the whole big thing, and then subtract. That's one possibility. There is another possibility. It involves breaking the donut. How could you break the donut? What if we cut the donut like this? If we cut the donut like this, we now have two donut halves. And then the bottom donut half would be beautiful for fix a value of x, and then y is going to enter, stay in, leave, and never come back. So one possibility is we could actually split it into two half donuts. Or we could add something in the middle and throw it away. So again, what I'm trying to do right now is just give you a little bit of a sense of what's coming as we go further. The more techniques we have, the harder the subject is because there's more things to try. So I think I've given you the example of crying baby, right? What do you do with a crying baby?
Like try it.
Yes. Yeah, I'm glad that you want to do something to try to make the baby stop crying, right? You go through your list of things. After a while, what should you hopefully be able to do? Distinguish the different types of cry. This is the I'm hungry cry. This is the I want to be held cry. And so after a while, you become an expert and you can immediately just know what to do. In the beginning, very hard. And you just keep trying everything until one works. The more techniques you have, the harder it is because it's not clear what to do. Does anybody know who the great Richard Feynman is? Nobel laureate in physics. When you know what the Challenger explosion was, he was the one who actually figured out why the Challenger exploded. And he, if you ever want interesting readings, I mean, I would advise you to read his textbooks on physics, which are phenomenal, but he has a lot of just, humorous anecdotes of his life as a physicist. And he had a very interesting life. He had a very interesting personality. He had a reputation for being able to do integrals that no one else could do. And when people were stuck, they would come to him and he would solve them immediately. And the question is, why is he able to do all these integrals so quickly when all these bright people at MIT and Princeton can't? And he said, well, I'm at such and such a school. I'm surrounded by bright people. If the standard techniques could have solved the problem, they wouldn't be here. So I'm going to assume they've already tried everything standard and everything standard has failed. There is a technique of integration called differentiating under the integral sign, which most people don't know. Let me try that first. And because, of course, if they could have solved it with the standard problem, they would have solved it. Most of the time he was able to solve the problems very quickly and got a wonderful reputation. So you really want to start getting a sense of which types of problems can you do and how can you convert anything to what you want. I can't integrate over a donut because that's a tough region. I have two possibilities. One is fill in the donut and now integrate over the large region and subtract, or split the donut into two half donuts where each region is nice. So a lot of the next few lectures are going to be talking about integration techniques. How do we take these spaces in several variables and split them to nice regions where we can integrate? This is a good place to stop. Welcome back again.